So we're going to talk about these further issues. And again, it's slide by slide, we talk about different topics. So you think that, okay, no, what are we doing? Why there's no connection? No, it seems that there's no connection between the topics that we cover, but it's okay. These are the purpose of the chapter is to put together different topics from different places. All right. So the first one, we will talk about the effect of data scaling on OLS statistic. Now, so far, I think the questions like this have been come up into your midterm 1, and you'll see one on midterm 2 as well. So there's nothing new here. You already knew that what will happen if the dependent variable is multiplied by some number. What will happen if the independent variable is multiplied by some number, right? But here I just put it, I summarize it and put it here. So if the dependent variable y is multiplied by a constant, then we know that all the estimated coefficients are going to be multiplied by alpha. Then the residuals and the standard errors are going to be multiplied by alpha again, but t-stat, f-stat, and r-squared are not going to change. Because, for r-squared, it doesn't make sense that if rescaling the parameters are going to, rescaling the variable is going to change r-squared, so you should not get a different model or goodness of fit for a model if you multiply basically the dependent variable to some number, right? It's nonsense. For t-test and f-test, we can mathematically prove that, right? So for instance, you can say, remember what was our t-test? T-test was, my beta hat j divided by, standard error of beta hat j. Now, I know if I multiply y by alpha, everything is going to be multiplied by alpha. So the new t-stat is going to be what? So alpha beta hat j. And what about the standard error? Standard error is going to also multiplied by alpha. Alpha is standard error of beta hat j. So these alphas will cancel out each other, so t doesn't change. For f statistic, you can give it a try. You can either use, if you use any of those formulas that we had for f, for instance, SSR restricted minus SSR unrestricted divided by degree of freedom or the number of restrictions, and then SSR unrestricted divided by n minus k minus 1. So if I multiply y by alpha, what will happen to SSR? Remember, the SSRs are going to be multiplied by alpha squares, right? Because these are the sum of squares of residuals or sum of squares. So this is going to be, let me use another color. This is going to be multiplied by alpha squared, and alpha squared. So these alpha squares will cancel out each other. So I can factor out the alpha square from the numerator and cancel it with the alpha square from the denominator. So t doesn't change, f doesn't change, r squared doesn't change, but residuals and standard errors are going to be multiplied by alpha. Variance, the variance of beta hat j is going to be multiplied by alpha squared. Okay. Again, these are not new. We have seen these things before. And then we're going to say that if an independent variable xj is multiplied by a constant, what will happen? This was a question for your midterm 1, so we already talked about it. If x is multiplied by alpha, then the coefficient of only that x is going to be multiplied by 1 over alpha, and none of the other coefficients of x's is going to change. So if x is education, if I multiply education by alpha, the coefficient of education only is going to be multiplied by 1 over alpha, and nothing else is going to change. The variance of beta hat j, residuals, standard errors, t-test, f-test, r squared, nothing is going to change. Okay. Now, the second topic. So again, we are talking about different topics. The second topic, let's talk about more on functional forms when you're using a logarithmic model. So when we use logarithmic functional form, these are the properties that we have. So why we use logarithmic functional form? First, it is convenient, because it's convenient percentage or elasticity interpretation, right? Remember, what did we have? We said that if you have log-log model, I'm talking about constant elasticity model, right? 1% increase in x, beta percent increase in y. So percentage. Then we talked about log level model. So log level model, we're talking about increasing return. For instance, we said 1% increase in education, 100 multiply beta percent increase in wage, right? Then we had level log model. So for the level log model, it was decreasing return. So let me call it decreasing return. And we call the first model, elasticity model, and the second and third one, semi-elasticity model. Okay. So this is, we use logarithmic because it's convenient. And when it comes to elasticity and percentage interpretation, and just as a, give you a reminder, this is data looks like this, constant elasticity. For log level model, you have an increasing return, so data looks like this. For level log model, we have a decreasing return, so the data looks like this. Yeah, this was another question for your midterm, for the midterm one. Okay, let me go over the rest of them because the second one needs an explanation. I'll come back to the second one. So the third one, taking log often eliminates or mitigate problem with outliers. It does the job because taking log is going to shrink the distribution. So if this is the distribution of it's going to be positive of my y variable, and maybe y is wage. So if I transfer to log, so the distribution is going to be shrink. It's going to be something like this, and it's more normally distributed. So if there's a chance that we have outliers in wage data, those outliers are going to be mitigated a lot in the log wage data. Okay, so we solve this problem. Then the fourth one, taking log often helps to secure normality and homoscedasticity. Again, this transformation is a very useful transformation, and we do this trick for variables in economic and finance that are, deals with large numbers, right? So for instance, millions of dollars for income, sales, things like that. So it's a good idea to do log transformation. And then and it helps to have a normal distribution for our wage. And if it is normal, we can deal with homoscedasticity as well. Okay, sometimes the data is heteroscedastic. We see if we do the log transformation, it's the distribution of the residuals are going to become normal, and then we can get rid of that heteroscedasticity. You've also seen this in one of the homeworks as well. You were supposed to look at the residual plot, well, histogram the residual for wage versus log wage, and you saw that for the log wage it was normally distributed. And then the fifth one is log must not be used if variable take on 0 or negative values. So this is not surprising, we already know that, because what is the log of 0? Minus infinity. What is the log of 0.5? It's a negative number. So we have to use log transformation only if y is greater than 1. I'm sorry, greater than, 0. We can 0 or negative. So we cannot use log for negative values or for 0. So 0 does not make sense. So I cannot use log for 0 because log of 0 is minus infinity. All right. Now let's talk about the second one. So how we can prove this one. So let me well, I can use the lower part of the page. So it says that slope coefficients of log variables are invariant to rescaling. And be very careful. It only says that the slope coefficient. So let me pull my highlighter. Slope coefficient. Okay, so let's talk about that one. We are going to use the property of log. So we know that log of alpha x is going to be equal to log of alpha plus log of x. All right, this is a property of if when alpha is a constant. We also know that the log of gamma y is equal to what? Log of gamma plus log of y. So this is a property of log. Now let's use that property in our regression. So let's say the base model is, let's use this color, is this one. I'm regressing log y on a constant plus log, then beta 1 log x plus, we'll call it x1, and beta 2. Well, let's keep it simple. This one's some errors. And with log of x, and then the rest of it is some error. So log of x plus some error. Now, if I multiply y by gamma and multiply x by alpha, then do you agree that I can use this property and write it like this, write the whole new thing as in this form. So log of gamma y is going to be equal to log of y plus, I'm going to use another color there, plus log of gamma, and this is equal to beta 0 plus beta 1 multiply log of x. Does everyone see that? Okay. And so here I'm going to open up this thing. Log of alpha x is going to be log of alpha plus log of x plus, well, there's an error at the end of it, and then plus what I have, beta 1 log of alpha. Okay. Now look at that. This is a constant. This is a constant, and this is my intercept. So I can put them all together and call it a new intercept and do not touch anything else. So let me rewrite the whole thing for last time. So log of y is going to be equal to beta 1 log of x plus u, and then add all those red numbers. So log of is going to be beta 0 plus beta 1 log of alpha minus log of alpha log of gamma. So let's call it beta 0 prime. It's a different thing. It's a summation of these three things. But when I say summation, it's technically beta 0 plus beta 1 log of alpha minus log of gamma, right? But look at that. I go from my original model, let me use green. I go from this model. When I multiplied x by alpha and multiplied y by gamma, and I ended up with this model. So it seems that nothing changes. You know, look at that. The slope coefficients, beta 1, did not change. It is still beta 1. The only thing that changed is my intercept. Okay, so this will show up in your midterm too. So pay very good attention. Be careful. Only the slope coefficients are invariant to rescaling. So the slope coefficients of logged variable only are invariant to rescaling. The intercept is not invariant. Be careful, okay? So this is a very cool property of logarithmic functional form, right? Because we know that now it's invariant to rescaling. If you just rescale, your coefficient is not going to change. So that was something interesting. Okay, now let's talk about the third topic. So the third topic, we're going to talk about quadratic functional form. So we have seen this quadratic functional form before. So we said that if the data is something like this, or something like this, we know that the linear fit is not going to do a good job. I need a nonlinear fit. So the nonlinear fit can be quadratic, right? So this is a concave version, this is a convex version, right? Quadratic. So how can I have something like that in the regression analysis? By putting the quadratic version of your exponential variable in the model, right? So let's go over and this is important. Quadratic functions are used often in applied economics to capture decreasing or increasing marginal effect. So the thing that I just plotted for you. So if you believe that there is increasing marginal effect, or if you believe that there is decreasing marginal effect, we can use quadratic functions, right? Now let's look at our example. We are regressing wage on experience and experience squared. Okay. So first of all, let's see how we can do it in R. Can I zoom in a little bit? Yes, I can. So too much. This is how we do it in R. So again, this is nothing new. You have seen this before. If you're regressing, I'm here. You're regressing wage on experience and experience squared. Make sure that you put this I thing, because if you don't put that, R gets confused. It's going to treat it as an arithmetic to that equation, and it's not going to look at it as a separate variable. So if you don't put this I, R does not understand that you're talking about experience score as a separate explanatory variable. Okay, so make sure that you put this I thing. And then the output, what do we see in the output? So let me zoom back. So it says that experience is positive, coefficient, experience score is negative, and it's significant. Look at that. Both of them are super significant. And our intercept is also significant. So look at the R score and adjusted R score, 9.3%, 8.9%. It's not good. It's not that bad either because we don't know the context of the research, right? But anyways, so this is what we get. So you're going to say that, look at that, because the sign of this experience score is negative, so we're dealing with a concave experience profile, right? So concave is what? So something like this. Remember, if I have y equals x squared, something like this. If I have y equals minus x squared, it's something like this. So we call this concave, we call this convex. So because the sign of the experience score is negative, then we're dealing with the concave experience profile. What does that concave experience profile mean? So in order to answer that question, we have to first calculate the marginal effect of experience. And I think I've said this before, that when you have when the explanatory variable on the right-hand side, it comes in a different functional forms like x squared, x cubed, x1 multiply x2, things like that. Whenever you want to interpret the coefficients, you have to take the derivative, right? So we have to take derivative with respect to experience and then try to interpret that. And again, this is not something new. We have seen this before. So let's take derivative of wage with respect to, with respect to experience and see what we get. So in this equation, let's take derivative with respect to experience. So this is 0, this is 0.298, and here minus 2 multiply 0.0061 multiply experience, right? So this is the derivative. What does this mean? This is the marginal effect of experience on wage, right? So how do I interpret that? I say that the marginal effect of experience on wage is going to be equal to 0.298 only if the experience is equal to 0, right? Or I can say, what is the marginal effect of the experience when the experience goes for the second year, right? So when we go from first year to second year. So when the experience is 1 versus 2, it means that we go from experience 1 year experience to 2 year experience. I want to see the marginal effect, right? So you say something like this. The first year experience increased the wage by some, 29 cent-ish. The second year is going to increase it by this number minus this number. Does that make sense? Because I have to plug 1 here. So this is, if I want to calculate the marginal effect of the second year of experience, I will set experience equal to 1 and see when I go from 1 to 2, what was the marginal effect of that second year. If I want to calculate the marginal effect of the 10th year, I will set experience equal to 9 because I want to see when I go from 9th year to 10th year, what was the marginal effect, okay? Let me zoom out a little bit. It's okay. So look at that. It seems that as experience is getting larger and larger, so let me erase everything. Focus here. As experience is getting larger and larger, the marginal effect of experience because of this negative sign is getting smaller and smaller. So something like this. Remember, what is marginal effect? That's the slope. So we have a concave experience profile. As experience is, and look at this slope. As experience is getting larger and larger, the slope is becoming smaller and smaller. And at some point, slope is negative, is 0, this point, and from that point further, the slope is going to be negative. Okay, so this is not good at all. So why do I mean that it's not good at all? Because look at that. We have a model. It seems that our model is telling a contradicting story. So pay very good attention to here. This is big. This is important stuff. So the model is suggesting that if, and let's say this number, let me actually cheat a little bit because we can calculate this number. It's 24.4. So we can calculate this maximum Well, I'm going to show it how show it to you how to do that. It's from algebra. It's easy. But let's say the model is suggesting if the experience is anything less than 24 years, then as experience increase, so let's say from 5 to 6, as experience increase, the marginal effect on the experience on wage is going to increase. It basically says that if you have less than 24 years of experience, yes, the more experience you got, the more wage you get. Okay. But from when the experience is greater than 24.4, the more experience you have, then the less wage you get. Look at that. The coefficient is negative. So it seems that as if the model is telling you a contradicting story. We don't like this idea. So how can we deal with that? So in order to answer that question, I need to see how many observations I have for when the experience is less than 24.4 and how many observations I have when experience is greater than 24.4. If there are very few observations in either side, as long as the model has a consistent, non-contradicting story, it's fine. I can have a quadratic version of the model. Does this make sense? I hope that you realize it's a big deal because, again, sometimes you are motivated or you're incentivized to just put a quadratic version, but don't do it blindly because you have to look at this plot that I just draw. It's called effect plot. We're going to look at it in the next slide and see how many observations you have from that minimum or maximum point. Okay, so well, you know how to calculate the max or mean of a concave function, right? So for a concave function, we have a maximum. For a convex function, we have a minimum, right? This is a quadratic. For any quadratic function, if you take derivative with respect to the variable and set it equal to 0, solve for that variable, you got it. So let me just solve it here for you once at least. Y is equal to beta 0 plus beta 1x plus beta 2x squared. Okay, let's say this is the model. Now, if I take derivative with respect to x and set it equal to 0, so what do I have? Beta 1 plus 2 beta 2x. So this is my derivative, right? If I set it equal to 0 and solve for x star, so what is x star? When I put it as star, it means that the optimal, minimum or maximum, it depends on the sign of the beta 2, is going to be equal to what? It's going to be equal to minus beta 1 divided by 2 beta 2, right? So instead of using this negative or positive sign, we don't care about the signs. We just look at the absolute value. So the absolute value of beta 1 divided by 2 beta 2. And beta 1, beta 2 are unobservable, so we will look at the hat version, estimated version. So this basically says that for whenever you have a quadratic functional form and your x star, the point that this functional form hits the maximum or minimum. In some cases, we're going to see that you will hit the minimum. And actually, we have an example for it in the following slides. Okay. And we can calculate that number, and then we should see how many observations I have to the left or right of that number. So in this example, the maximum happens when the experience is 24.4. Okay. And now let's see, what do we have? Does this mean the return to experience becomes negative after 24 years? The answer is yes. Okay. But not necessarily. It depends on how many observations in the sample lie right at that turnaround point, right? Because if I have 0 observation here, 0 observation, then are you worried? Is the model telling you a contradicting story? No, because, well, it seems that on the paper or in theory, the model is telling you that, oh yeah, marginal effect increasing, marginal effect decreasing, so it's bad news. But if you don't have any observation here, are you worried? No. So there's only one consistent story that the model is telling you. Now, how can I know how many observations I have here on the left or how many observations I have here on the right? There are 2 ways. So in R, it's simple. So for instance, you can use that filter function, imagine I have a data, this is my data frame, $ experience. This is the experience vector, right? I just need to check, how many of them are less than 24.4 and how many of them are greater than 24.4. and then count them, and then divide by total number of observation and say the percentage. So let's say there's 3 of them and I have 100 observations, only 3% is on the right hand side. Okay, so no big deal. So this is one way. There is another way which is a lot simpler and using effect plots. So let me first give you the answer, and then we're going to look at the effect plot. So in this given example, there are about 28% of the observations on the right hand side. This is a big deal. 30% of the data is here, right? And then 30% of the data is here. We don't like it because now if I have experience square in the model is telling me a contradicting story, not for a small chunk of data, for 70% versus 30% of the data. This number is huge. You don't like it at all. Okay. So what can I do? This is a specification problem. So the things that you can do is most probably you're having omitted variable bias. Let me go back to the previous slide. What's going on here? Look at that. I'm only controlling for experience and experience square. So if I add education, age, and then, I don't know, gender, female, and lots of other controlling variables, the odds that this number, this threshold is going to, sorry, this threshold is going to increase. It's going to be a lot higher, and then I have very few observations here. So that's we call it a specification problem. So you can deal with it like that, but be careful. Whenever you want to use quadratic, you have to do the effect plot and see how many observations we have. And what is that effect plot? Next slide. So I say it's optional, but honestly, it's one line of code in R. So just take advantage of that power so you don't need to calculate things manually. So there's something, what you see here, this is called RUG plot, R-U-G, RUG plot. And what we see collectively here is effect plot, okay? So in order to get the effect plot, you have to install a package. The package is called effect. And then, of course, install the package once, and then call the library effect. And then first, you need to save your regression object. So imagine I'm regressing wage and experience square using wage one dataset from Wooldred, call it MRM. And then the function that we use in R is super simple. Plot, then open close paren, effect, the variable that you want to see the effect plot for, and the name of the regression. Okay. So be careful, this is character, so you have to put the name of the variable exactly as it shows in the model. So if it is experience, just do experience. If you want to look at the effect plot for education and you have education in the model, do something like this, and etc. Okay. And then you have to pass the name of the regression. If you do that, it will give you something like this. So first of all, by looking at this effect plot, you can get a sense where the maximum is happening. So it's around 25-ish, okay? You don't need to be exact. If you want to get the exact number, you have to take derivative and set it equal to 0 and solve for it. So the way that we did in the previous slide. But here, again, we can do some quick eyeballing and say, okay, this is 25. And now look at the RUG plot. It seems that there are many observations on the right compared to observations on the left. So by looking at the effect plot quickly, you can say, no, the marginal effect of experience, because this is the experience effect plot, on wage is telling me a contradicting story, and I don't like this one. So what is the solution? Either get rid of experience from the model, or add some controlling variable, add education, add gender, etc. Do not leave the model like this. This is not a good model because it's telling you a contradicting story. All right. Now let's talk about another example that it's a convex function. So usually when you're adding a quadratic version of a variable in the model, you need to control for more explanatory variable. The reason is that we talked about it here. If I don't control for explanatory variable, I will get this problem, which we don't like. But if I control for more explanatory variable, the chances that this happened at the end of it it's going to be higher. It depends if it is concave or convex. It can be here, it can be, if it is concave, it can be here or here, right? You're getting closer and closer to the edges, hopefully. And then the observations that we see from that cutting point is small. Okay, now let's look at this example. We are regressing log price on log NOx. NOx is basically nitrogen oxide in the air. So it's a proxy for pollution. The more polluted area, what happened to the price? You expect to see a lower price, right? It's not surprising. Distance, strat ratio, oh, this is a student ratio, but anyways, well, distance from employment center, if you're further from the employment center, maybe the price is lower, so that's why we see negative sign. And finally, average students per teacher ratio. If a student per teacher ratio is high, so it means that we have fewer teachers per student, so maybe it's in a lower quality neighborhood, so we expect to see a negative sign here as well, right? But anyways, these are the controlling variables that you're putting in the model. What I'm interested is to look at room, right? So we're going to say that let's have room and room square in the model, because you believe that the marginal effect of room on the price is not going to be constant. You believe that it's either increasing or decreasing. Actually, you think that it's going to be increasing, right? Because, again, you are a researcher. If you believe that's the case, you are going to set the question like this. You want to say that I need to have a quadratic version of rooms in the model. Basically, when you're doing something like this, you believe that the more number of rooms you have, the marginal effect of additional room on the house is going to be higher. Okay? Maybe in your mind, you think that it's going to be completely the other way around. So if I go from 5-bedroom to 6-bedroom, I expect to see the marginal effect is going to be negative, not positive. So, or not negative, increasing a decreasing rate. Okay. But anyways, in either case, you don't know the signs yet before you run the data into the model, right? When you don't know the sign, you just leave it in the model as a quadratic version and then let the data decide that if this sign is positive or negative. In this case, it seems that the data decided that the sign is positive. So the data is suggesting that we see something like this. Okay. Again, maybe you think that it's counterintuitive, but this is what the data is suggesting. Let me quickly review that counterintuitive things, because if I ask you, what do you expect to see? If you go from 2-bedroom to 3-bedroom, the price of a house increase more or less than if I go from 6-bedroom to 7-bedroom. You might want to say that, well, of course, when we go from 2 to 3. If you believe in that scenario, you'll see something like this. But here, the data suggests that this is positive, room score is positive, so we are seeing something like this. So now you are left kind of baffled. You want to say that, okay, what's going on? My intuition is kind of correct, but the data does not support that. So in research, in real world, when you get to points like this, you have to sit back and look at the data. So you have to dig data more and say, okay, what's the minimum number of bedroom? What's the maximum number of bedroom? If the maximum number of bedroom in this data set is only 3, then yes, it makes sense. Maybe 1 to 3, 2 to 3 has more effect than 1 to 2 bedrooms, right? Again, so this is one case. And then, so in general, be aware, sometimes your intuition is not supported by the data. Okay, so should I stop here and say, okay, because this one is significant, this one is significant, then it means that I should add the room score into the model? Don't jump into conclusion. You have to look at the effect plot and see if the model is telling you a contradicting story or not. So let's do that by doing the effect plot on next slide. Okay, so well, actually effect plot is the next 2 slides, but let's do it manually and then we'll see. So if you want to take derivative with respect to number of rooms and set it equal to 0, so this is my derivative, right? So the derivative is suggesting that if the number of rooms is 0, then the marginal effect of room on price is negative. This doesn't make sense. So we have to start from a positive number, right? So, and it says that, okay, if the number of rooms is 1, still it's negative. If it is 2, still negative. If it is 3, well, you know what? If you calculate this cutoff point, it's going to be 4.4. This means that the model is suggesting as long as the number of rooms is less than 4.4, then additional room is going to have a less impact on the, or negative impact on the price of a house. Okay. If the number of room is greater than 4.4, then the additional room has a positive impact on the price. Okay. So for instance, let's look at the marginal effect. Then we go from 5 room to 6 room. So this is the marginal effect of the 6th room. So I need to plug 5 in the model, in the derivative. Minus 0.545 plus 0.124 multiply 5. Again, this is a marginal effect of the 6th bedroom, which is positive. And how do I interpret that? Look at that. We have log price versus bedroom. So 1 unit increase in bedroom, what percentage increase in the price? So if I go from 5 bedroom to 6 bedroom, then the marginal effect of the 6th bedroom is going to be plus 7.5%. If I go from 6 to 7 bedroom, it means that what's the marginal effect of the 7th bedroom? 20%. Okay. Now you can do the same when the rooms are less than 4, and you see that effect is negative. You're going to say that if you go from 3 bedroom to 4 bedroom, so this number is going to be negative. So the effect on the price is going to be a negative percentage, percentage wise. Okay, now let's see how many observations I have on the left, how many observations I have on the right. Okay, so for that, we're going to use the effect plot. Very good one. So look at that. It seems to me that the minimum is happening here around here, 4.4, right? So we know that the minimum is at 0.44, 4.4. How many observations I have on the left? Only 2 or 3. Very good news. Most of the observation is on the right. So this is awesome. Okay, good. So I don't have misspecification problem. So the model is not telling me contradicting a story. It's telling me that as long as the number of rooms, and by the way, okay, I should have explained it earlier. This room is not bedroom. It's the number of rooms in the house. So kitchen, bathroom, living room, these are all rooms, right? So that's why we see this number 4.4. And now it makes sense. So originally, if you thought that if this room is bedroom, you said that, you know what, if it is bedroom, I should see something like this in the model. But now we know that this is not, this is the point that I told you that you have to dig more into data. Now rooms means, you know, any kind of room. If it is any kind of room, now it makes sense. If I have more rooms in the house, then the marginal effect should be positive, and it is positive here. Isn't it nice? So should I leave the model like this? The answer is, as long as this is significant, yes, of course add a quadratic version, because let's see. Look at that, significant. Definitely when it is significant, it's going to increase the adjusted R-square. We're going to talk about adjusted R-square in a couple of following slides. This is not a topic from this chapter. All right. So I found this effect plot very exciting because, you know, this is the story of your model, right? And you hope that you're consistent throughout the model. All right. Let's look at more examples. So imagine we can have a quadratic version, combination of quadratic version and log at the same time. So let's say I regress log price on log Knox and log Knox to the power of 2. Okay. Please don't do something like this. So this is a common mistake that if you do, you will get a perfect collinearity in the model. So if I write this like this, so let me see. Let me see if I'm missing anything from the previous slides that I wanted to say. Okay, no. So if I write this equation like this, what's wrong with that? If I say, okay, log price is equal to beta 0 plus beta 1 log Knox plus beta 2 log Knox squared plus etc. What's wrong with this one? Be careful. This is the whole log Knox to the power of 2. This is log of Knox to the power of 2. Do not make this mistake. Why? Because if I use the property of log, so what do I have? This 2 can come out. So I have 2 beta 2 log Knox. And then here I have beta 1 log Knox So what do I have? I have beta 1 plus 2 beta 2 log nox. I don't have a quadratic version in the model, right? So this is wrong. Make sure that you put this square outside of the log. And when I say make sure, it's you're not writing it down, you're typing it as a code. So your code should be I log nox to the power of 2. Okay, something like this. The whole log nox, if you wish, you can use extra parentheses to make sure that nothing is wrong. Okay, don't do something like this, log nox to the power of 2. Okay, this is wrong. This is correct. Okay, so then imagine we have log nox to log nox square, crime, rooms square, and student over teacher ratio. Then we can look at the marginal effect of log price on log nox. Okay, and I need to take derivative with respect to log nox. So think of log nox as a new variable z, and whenever you see z, log nox, just write z. So what I have, beta 1 plus 2 beta 2z, beta 1 plus 2 beta 2z log nox. Then you can plug some numbers and see what will happen. Then another example, higher polynomials. So we can have, so for instance, we can regress cost on quantity, quantity squared, quantity cubed. Do you think that, okay, without telling you any more information, without giving you any more data, do you think that this is a good specification problem, a specification in the model? The answer is no, because I'm not controlling for any other explanatory variable. And if I plot the effect plot for this quantity, this is to the power of 3, depending on the sign of beta 2, beta 3, then it can be something like this. So the model is telling me different stories at different stages, different levels for quantity, right? If the quantity is greater than this number, increasing. If it is less than this number and greater than this number, decreasing. If it is less than this number, increasing. So I have a contradicting story throughout the model. Most probably, I have many observations at any level as well. So I need to control for some other explanatory variable to make sure that something like this, not necessarily not happen. It may happen, but with lower probability.